So let's look at some examples of discontinuities. All right, so here we're going to find any x values at which f is not continuous, and then classify the discontinuities as, it should be discontinuities. As removable or non-removable. Okay, so f of x equals x minus 1 over x squared minus 4x plus 3. All right, so basically discontinuities here, what I'd be looking for, I'm going to primarily look for places in rational functions here where they're not defined, and I'll generalize that coming soon. So the idea here is, let me look at this factored. I get x minus 1 over x minus 1 times x minus 3. Okay, so I automatically see, I know that there are a couple points not in the domain here. All right, x equals 1 and x equals 3. So they're automatically places where the function is not continuous because it's not defined there. Okay, so now I have to figure out what exactly is going on there. All right, so x equals 1 and x equals 3. So at x equals 1, we see what we had seen in a lot of limit calculations. We have a common factor on top and bottom, which potentially in a limit situation could be canceled. So what that tells me is that it's a hole there. And a hole would be removable because all I would have to do is really fill in the hole. For x equals 3, what I'm seeing is a place where the denominator is 0 and the numerator is not. That's a vertical asymptote. And a limit doesn't exist at the vertical asymptote. This is non-removable. Okay, if you're wondering what the graph of this would actually look like, just to link up those ideas from before, you'd basically be looking at something like this, where there's 3. The function would be, would be like this. Okay, where here is 1, so there's your hole at 1, a removable discontinuity, and there is your vertical asymptote at 3, your non-removable discontinuity. Let's move to the next one here. Okay, f of x equals absolute value of x plus 2 over x plus 2. Okay, so I probably want to see this function out of its absolute value form. So the idea is that if this is all going to have to do with how where we are in x related to -2, because -2 is where this absolute value has that notch, and therefore it's a big difference between what's less than -2 and what's greater than -2. Okay, so if x is greater than or equal to -2, then what's going to happen is the absolute value doesn't have any effect, and I just get x plus 2 over x plus 2, so the function gives me 1. If I'm less than, oh, wait, careful. I got to go back for a second here. I'm not allowed to be equal to -2. So I have to get rid of the or equals to. So if x is greater than -2, then this would be 1. If x is if x is 0, we can't, if x is -2, then the denominator would be 0, and that's no good, can't have it. If x is less than -2, then the absolute value is going to take a negative number and make it positive. And so it's not going to be exactly the same as x plus 2. It's going to be off by the sign, so I would get -1. All right. This is one of those classic examples of the two lines not meeting up. So what I have is, at -2, I have, well, this value is 1 there, and this is -1. I have this situation. Okay, and so what we see is that we definitely have a discontinuity at x equals -2. And what's happening there? Well, the limit as x approaches -2 of f of x does not exist. Therefore, this is non-removable. If you want to think about the game we were trying to play, there's no point that I can put in. There's no point value that would connect these graphs up and make them continuous. All right, how about f of x equals 3x squared plus 1? All right, nice polynomial there. So what I'm trying to do is think about any place where the function wouldn't be defined. It's defined everywhere. Any place where the limit wouldn't exist. Well, the limit's going to exist everywhere because any limit value would be a calculation of plugging in, and it's actually always going to equal its function value. Well, this is continuous everywhere on the real numbers. Okay, a graph of this, again, you would just see this is just a parabola, and it's perfectly continuous. Okay, so can we generalize this? Yes. So let's see about some common functions we know. Polynomials are continuous everywhere. That means continuous everywhere on the real line. All right. How about a rational function? Any rational function is continuous wherever it is defined. That is continuous on its domain. Let's go back. The first example here was a rational function. And we noted that, or well, we seem to end up saying that the only places where it had discontinuities were on points that were not in the domain, places where the function wasn't defined. Now they had a different effect of what was going on there, but that we could have easily just said x equals 1, x equals 3 are the discontinuities, and that's correct. Okay, so polynomials and rational functions seem pretty easy to find discontinuities. Well, in general, it's not that bad. So a more general theorem here says the following type of functions are continuous at every number in their domains. Okay, and that's the key. So all these functions are continuous where they're defined, but they may not be defined everywhere. Anywhere they're not defined, they must be discontinuous. But the idea is that if you know where they're not defined, then you know the only instances of discontinuity. You don't have to worry about anywhere else. Well, polynomials, we said, they're defined everywhere, and so they're continuous everywhere. We just made the point about rational functions, but even root functions, trig functions, inverse trig functions, exponential functions, logarithmic functions, all of those are continuous wherever they're defined. So the problem of asking when they're continuous for those functions is just equivalent to asking when they're defined. That's not too bad. Okay, but how do we get all these discontinuities? Well, what we're avoiding here is we're avoiding basically putting these together in piecewise manners. A lot of our discontinuities that using these functions come from when they're put into piecewise functions and the pieces don't meet up nicely or how we expect them to in order to get continuity.